Okay, so cluster idling and brief update on what's going on in that. And I want to spend most of the time discussing what to do next and the current limitations there is in the series that I've been working now for a long time. Yeah. So just a quick recap, so to get everybody on board. So a while ago we started working on this, and more or less the topology we have is a bunch of CPUs being grouped into various clusters or whatever you want to call them, and there is a bunch of other resources coming into play as well. Might be shared with the cluster and whatnot. So when we look at this a couple of years ago, we realized that the CPU idle framework is not really a good fit for it. We need some kind of extension to deal with this kind of topologies from the CPU idle and the cluster idle point of view. So then we started playing with different solutions, and Linaro from Qualcomm was working with us with this a while ago, and I picked up the work from her. That's a while ago. So exactly why we need this is that we have platforms out there, both legacy platform, ARM platforms, and new platforms. So we're not only talking about legacy, but more or less it's the problem has been there for a long time, but it still exists for new platforms. And in principle, it's that when you go into a cluster idle state, you have a firmware, of course, that in many cases, but the firmware is not capable of dealing with all the things that you need. So you have to have take care of some last man activities on the system to be able to reach this low power state of the cluster. And in some cases, that's at least the only thing I've heard of is the Qualcomm. They have caching some of the sleep states of the platform, of the devices in the platform on the Linux side. And when they do this, moving to this cluster idle state, they are pushing these cached states into the firmware. So that's probably, it might be specific to Qualcomm, but yeah, it's still it's a case. And especially for legacy platforms, ARM legacy platforms, it's very common that you have the power rails that's powering the cluster might also be shared with other resources on the platform. So it could be more or less any devices, and on old platforms it could be quite many devices that shares the same power rail. And to my knowledge, it's also in some cases even a configuration on a platform level. So it might differ depending on how the SOC is being deployed for that platform. So in some platform there's some devices being shared, and some others not maybe not anyone being shared at all. So to deal with these kind of situations, when these kind of devices are being used, like an MMC transaction is going on, for example, you cannot allow the cluster to be powered off. So somehow that needs to be communicated in the system. So the idle path, so to say, does not power off the cluster, because that would break the MMC transition because of losing register context. So what we did is that we played with this generic PM domain, and a lot of changes has gone into that to cope with CPU devices, because it's designed for generic devices, so to say, but CPUs is a little bit special. we're, for example, running this idle path in atomic context, and yeah, all that kind of stuff that comes with it has been, we'll be extending the NPD infrastructure code to cope with these kind of special scenarios. So there is still a couple of things that's not upstream yet, but a lot of things has gone into that already. So that's one of the things, and the other part is the changes that we've been doing on the governor level. So we have the CPU idle and the CPU idle governors, which pick states on a per CPU basis. But when you have a group of CPUs, you need to pick a state on per group of CPUs, and that's what this MPD governor is doing. So it takes into account the sleep durations for a group of CPUs, and depending on when the closest wake up is for the group of CPU, you can pick an idle state based on that information. That's in principle what this NPD governor is doing. And part of this solution is also still using the CPU idle framework to let it take decisions on the idle states that is per CPU, so to say, the core CPU idle states that is still left to the CPU idle to do. Then on the backend part in the low level behind this, that's when the MPD infrastructure things kicks in. And this is based on this runtime PM framework as well. So you get the reference counting there in behind the CPU idle frameworks. So that's in principle how it intends to work, or how it actually works. And then you have to do some kind of platform deployment as well. What we have been focusing on is the PCI firmware, and that's one of the backends for CPU idle driver. So we have deployed this for PCI. There's DT bindings and all that stuff coming into play here, and so more or less the only changes that you need to do is to change your DTB, and then all this stuff just works for you, if you're using PCI, of course. And the platform that we've been playing with is mostly high key and Dragon Board 410C. That's those boards I've been playing with, but I recall a while ago we also had a MediaTek platform where we tried this out. So that's what we've been doing in the past. And the latest status is that there is a V13 of the series on the mailing list, and there is 4 patches which provides the core changes that is needed on this MPD level that is left to be merged. And lately, both the maintainers are happy with the series, and Daniel has reviewed it as well, so it looks good. No outstanding more changes that seems to be done, unless there's new reviews coming in, of course. On the deployment side, the PCI side, there is a cleanup series, which is more like giving the foundation to do the actual deployments. That's been reviewed and agreed on that this should go in, and then on top of that, there is another 18 patches or so for the deployment part that needs to be reviewed and act, and we'll see what happens with that part. I'm going to post those changes as soon as any of those other series gets queued up. So that's probably hopefully next week or so. And if you want to play with this, there is a couple of Git branches that you can use, and the next branch that I'm pointing to here is the branch that we are using in our we have an integration tree for power management, the power management working group, where we share our work in progress things. So this is being merged into a common integration branch where we do some automatic CI tests, more or less. So that's a branch I try to keep up to date in based on the RCs that exists for the moment. And if you want to look at the edge of the changes and the absolutely latest changes, you should look at the next and the V and the version. And in this case, there is a V13 branch, and that's based on the Raphael's Linux PM3. So that's not, it's absolutely on the edge, so to say. Right? Any questions on that?
Do you have some description of what code did you move from the firmware-based one-man standing? What's the changes, the main changes?
How it actually works?
Yeah.
So I don't have those kind of slides here. If you want to, I can bring it up, if you're keen on the details.
Performance implications,
So there's a whole bunch of limitations, and most of the limitations is concerned about latencies. That because you have to take care of this last man standing thing, you have to have locks. And it's more or less a spin lock that you have to have. The thing that we're trying to avoid is to keep this spin lock for a long time. So it just takes the spin lock and do the necessary action and releases the spin lock. So it actually opens up for a small race, but that race is going to be, that race needs to be taken care of in the PCI firmware anyways. So we have a per CPU variable where you have this information about the cluster states, more or less, and you communicate that to the PCI firmware, and then you leave the decision to the PCI firmware to take on what kind of operations you need to do.
So this eliminates the need for another CPU or firmware-based that does this cleanup stuff. So you don't really need another small CPU to do the handling of what standing for each cluster.
So you need to deal with the race conditions in the firmware, but Linux helps out dealing with last man standing things. Yeah.
So you remove most of the dependencies.
Yes. Yeah.
Does it mean when you are reaching the barrier, you have to do busy looping with the spin locks, or?
Yes.
So it doesn't.
That sucks.
It doesn't consume more energy than.
So the problem is this is a functionality you get from the platform design. So you cannot have. So when you wake up, for example, and all the CPUs are in a low power state, cluster idle state. When the first CPU wakes up, there is a bunch of first man standing things that you need to do before you can start executing the other CPUs anyways. So you have to sleep there. There's no well, some platforms have to sleep there, of course. It's not like it's common for everyone. It depends on the platform, of course. But for this platform that has this kind of design limitation, that's what you have to do. So you have to take care of all this. You have to restore some power rails, and you have to restore some PLLs and stuff.
I understand. I'm wondering if it's not possible to have a lockless.
So what will you do when assume CPU 1 is waking up and all the other is sleeping, and CPU 2 is waking up as well? What shall you do?
You can take lock, but without spinning. That was the.
So some CPU needs to wait for the other CPU. How do you deal with that?
Don't remember, I have to look at the code I wrote. But in the snowball, if you look at the snowball, the last man standing,
But
what is the difference with the snowball?
The snowball is not reaching the cluster idle state. The code that you've written there in the CPU idle driver is not reaching the cluster idle state. It's just retention. So it's nothing more. It's the spinning part there is really quick. But if you reach the real low power state for the snowball, for example, then.
But at the moment the CPU enters the idle loop and it decouples the GIC.
Mm-hmm.
You know that you won't be wake up, so you have a critical section where you are you are safe to be synchronized without spinning, busy looping and spinning.
Yeah, so there is room for optimizations more or less. But when you wake up, you need to wait. There's nothing that you can do about that.
Okay, because I'm just worried about what happened with the couple C state, which is putting barrier with spin locks.
Yeah.
And when I tried that with 4 cores, couple with 4 cores.
So in the ideal scenario, those other CPUs shouldn't wake up, and it shouldn't wake up. It could be, if you talk about legacy ARM platform, if you got things right, you might have these kind of cases where you can decouple the geek, so you actually avoid these to wake up. But if you don't have that kind of, hardware things, now I lost myself. So if you wake up, no, sorry, completely decoupled. So the thing is that.
So you mean as you can decouple the CPU, you don't have to wake ups and being spinning loop always with the barrier or exiting and entering the states?
No, so what? Yeah, exactly. But if you don't have that kind of facilities, the other CPUs might wake up because you have predicted something wrong, right?
Okay.
Yeah. So I mean, I don't know how to deal with it. It's like a hardware constraint, and you have to wait somewhere.
Okay, so you have the key. It's the decouple thing. If we because we can decouple, we don't have this situation where you have some.
But it's very platform specific if you can do that.
Okay.
That's like in this case for Snowball, for example, that's possible. But that's probably a very specific case. So in this deployment that we did for PCI, all this kind of stuff is happening in this back-end part of this NPD driver. And what we do there is that we take the spin lock and checks if we are the last man. And if we are, then we update the per CPU variable and then just release the locks. And then when you actually goes into the idle state, you request PCI firmware to take care of this. Then you take this per CPU variable and add it on top of the state that you have selected. The CPU idle state is going to be added with the cluster idle state, more or less. And then you put that as the complete state that you push to the PCI firmware. So potentially, because you have released this spin lock, another CPU could wake up in between. And if that CPU wakes up, the firmware should know about it. So when it gets the request that the request is to go to a cluster idle state, the firmware knows that, oh, I cannot go to cluster idle state because this other guy here is woken up, so I should return an error code to that. Okay. So removing part of this contention to deal with this in the firmware. That's something we have to do in this solution. Otherwise, we'll be spinning even more. We don't want to keep the spin lock while we are sleeping, of course. That would be even worse. Okay. So this is more related to comments that we received on the series lately, and so this is I think this is the most important update that we did for, maybe this was V10 or I don't know exactly, but earlier we were focusing on deploying this for this PCI OS initiated mode. I don't know if you have the knowledge about PCI in detail, but it's a slightly different way of how you communicate the cluster idle states to the firmware. So we realized that this was actually not very good to have that limitation in the series. So instead we took a step back and made these bindings that we invented to describe this topology of the idle states completely orthogonal to whether that's supported by the firmware or not. So I think that's the main changes. So if you want to convert to this new binding, it should just work no matter what the firmware supports or not. So that's the main changes that we've done recently to the series, if you're into the details.
And these give you the advantage that you will have the knowledge about which CPU are belonging to which CPU is sharing the power domain.
Yes, yes.
With another CPU.
So even if you have OS initiated mode or platform coordinated mode,
Yeah.
you might be interesting to take to do last man activities for that particular platform. So this allows you to do that.
So where can we find more details about the architectural specific bits in this, the software architectural specific bits,
How you use it.
how you use it and how the entire thing is set up?
So it's we've been having this talk for several years now, so I actually skipped those parts because I was more or less expecting people to have some background knowledge about it. But I mean, I have a bunch of slides I can share with you for earlier talks. I can give them to you. Just yeah, we can talk about it later, and I'll give it to you. There's more more diagrams and more that kind of stuff that I can probably explains a little bit more how it actually works beneath. Yeah. If there's anybody else wanting these, I can share them in some good way.
So, and what is interesting is that now, I mean, yeah. So you have this cluster idling, or you have this power domain hierarchy, which is available in both, whatever the mode that is used. Even if for the coordinated mode, it's more just informative. I mean, there is no real cluster of decision taken by GenPD, but at least everything is there and available.
So what's the reason why you want to use this for platform coordinated mode is that you want to be able to take you want the ability to do these last man standing operations. So that is what GenPD is providing you. So there is this reference counting going on. So you know when the last CPU, when all CPUs has voted for a cluster power down state, and you know when the last CPU is going down with that voting mechanism. But the actual state selection process is done by CPU idle as before for that particular mode. So that's so this is taken care of when you initialize this power domain structure and put the devices in that structure. You will have a knowledge of whether the PCI firmware supports OS initiated mode or not, and depending on that, you will do different actions there in that path. So it's okay. So, as I said, there is a bunch of limitations and improvements that we can make. And one thing that is not there yet in the series is that when you do this cluster power down thing, you want to do these last man activities. There is a callback that's being invoked today, and that's provided by this GenPD infrastructure. It's like a power off callback. But today, we only deal with this, the PCI-specific bits, so to say. So in principle, you want to notify, or you want to call some functions to do this last man standing things. And to do that today, there is a cluster PM enter exit function that's exactly provided in the kernel to do these things. And this is already used by, I think it's 3 or 4 platforms today. It's not using this solution at all. They have their own way of dealing with cluster idle states. Specific platform-specific CPU idle driver and some back-end parts to that deals with this. But so potentially we could just make use of that going forward as well. It's already there and it works. But I have some concerns about that in the long run. And my concern is that there is no communication what kind of state you're entering, just a cluster idle state. So do you actually have to notify about all cluster idle states? That's one thing. The other thing is that there is no way to actually take into topology consideration here. So who is actually the consumers of this notification on that particular platform that is running? So it's like just a software way of my consumer are interesting of this notification. So I will register myself, and that might be correct for one platform, but might not be correct for another platform. So there needs to be some kind of topology described here, and maybe that's DT that should solve that for us. So for that reason, in the long run, I think we need to explore this YMPD on-off notifiers, domain on-off notifiers, I should say, because YMPD has this topology information, and you can also describe this in DT already today. So somehow I think it makes sense to explore that path. That would also allow you to actually provide what kind of idle state that you're interested to consume. So that's one of the things I'm looking into, of how we can move forward, so to say. But short-term wise, we could use this existing enter-exit function for the cluster. But it's not part of the series, so it's just more or less just one function called, or two, enter in the off callback and on in the on callback. When it comes to system suspend, and in particular suspend to idle, this series is trying to do a best effort there, but it's not really picking the lowest idle state as you expect from suspend to idle. So there is a couple of things that we need to look into this. Union has been working on the platform to try this out, and yeah, there are some problems there that we have to look into. But the main thing here is that this entire cluster idle state selection is based on that runtime PM is used. That's the one that deals with this reference counting things. And when you go to suspend to idle, that's quite late in the system suspend process. That means that runtime PM has been disabled for all devices in the system. So that means that these kind of reference counting isn't working anymore. In the normal cases, YMPD deals with this because it has its own internal reference counting for system suspend callbacks. But in this particular case, we have these per CPU variables, and that's not something that's needed for the regular cases of devices in YMPD. So we need something else here to deal with CPUs. That's missing in YMPD. I have a couple of ideas, but
what you are saying is that if the GNPD is in charge of the last man activity for the CPU, we will have this problem with suspend to idle.
yes.
But if we are using the coordinated mode, we are safe in the sense that
Yes.
okay.
Yes.
because the final decision is taken at the firmware level.
Yeah, yes, exactly. There is one problem with the platform coordinated mode as well. That's you might have these last man activities things.
Yeah, if you have some additional things
Yes.
that you need to do.
So, and if those activities needs to be executed on the last CPU, from the last CPU,
Yeah.
there's no guarantees in that.
Okay.
When
Yeah, you don't have anymore this to be
Last-
the last one.
Exactly. You know that there is a last one, but it doesn't have to be the one that is actually the last.
Okay.
So it's, yeah. So it's broken in that regards, but
Okay. Right.
Hmm.
But that's probably not a major problem for now, for sure.
I don't think so, no.
Because you're using the coordinated mode, so for
It's-
that you're safe.
Yeah. So yeah. Yeah, there is a couple of solutions on how we could fix this, and yeah, we have to look into that. So that's future work that we have to look into. I think we're moving into a little bit more of a optimization things here that I've been considering. And in the idle path, when you do the state selection, using k-time get can be a little bit costly, so you don't want to do that too often. And in the regular idle path, we have one k-time get being called in the core part of the idle path, and that result from that is actually being shared through the different layers in the idle CPU idle. We have no, so yeah, in principle we would like to reuse that somehow, but to reach that point, yeah, I think we need to have several steps. And initially, I think we can start looking into all the calls to get k-time get in NPD and see if we can drop some of them, or well, optimize them away in some way or the other. There is a metric in NPD doing measurements for each of these runtime PM calls that enters NPD, and the measurement is kind of silly for CPUs, so we don't want them for CPUs. For regular devices, those measurements are done to understand how long time it takes to suspend and resume a devices, and those measurements are then later compared to so-called dev PMQS constraints, which is it's a bit silly for CPUs to do that.
You're right. That you have this auto worst case latency wake up.
Yes, but we do measurements every time.
Yeah, so yeah,
So
clearly
it's
this should be disabled.
Yeah, so there's a lot of k-time get being done in that path, and it's really silly for CPUs.
Yeah.
And actually it might be silly for regular devices as well. So I've been considering a long time ago that maybe we should have like a calibration phase. So when you do this calibration, then you just turn off these things.
Yeah. Or even is there is no flag to say I want to have this auto calibration
it's always
feature?
on. Always
Okay.
on.
Yeah, maybe we should be able to disable for the device.
Yeah. And another thing that we did in the runtime PM core recently is that we converted from to HR timers to do this kind of similar. It's not exactly for the same purpose, but it's there is timestamps taken to understand how long a device has been active and non-active, and then we converted to use this k-time get mono fast, which is a lot faster than k-time get. So it's we can also start looking into doing that kind of changes to NPD.
So it's not that much faster.
It will not be acceptable for CPUs, but it might be an improvement for the generic devices.
Yeah, normally the k-time get mono fast should be used only if you can be involved in the timekeeping process. Otherwise, there is not that much performance difference between both. I can't remember exactly, but I mean, it's not 10 times faster.
Okay.
There is probably, maybe in the worst case, you can reach some 30% of difference.
Okay.
But most of the time, that should be really negligible.
Yeah.
It's just that you have only one write sec sequence in the k-time get monofast, whereas for the k-time get you can have 2 levels. the first one when you're updating, and to take into account the case where timekeeping is updating your clock deviation.
Okay.
In any case, that the local clock or time gate is
Big difference.
there is no big difference. There is a difference, but not so big.
Local clock?
Local clock and time gate. It's not. There is not a big difference.
You can have some difference on the max value.
Ah, okay, yeah. So, but local clock is not possible to use for MPD.
No.
No. But yeah, it's quite close in terms of performance. It's a bit slower because you have this, I would say, these two additional tests.
Okay, okay.
But I would say in average, it's not that.
So yeah, more or less the conclusion is that we don't want anything of this to happen for CPUs.
Yeah, it's mainly that.
Yeah.
It's useless.
But for CPUs, we can reuse what we already have. I
The
mean, because that's,
existing.
yeah, because the time gate is done in several places, and for example, when you enter idle, you have a time gate already done.
Yeah, that's. I mean, that's the one that value we should be able to reuse and pass on. Yes. That's my idea as well.
Yeah, and
so that's the long-term goal.
But what resolution do we want for the? What resolution do we want for the not the CPU but the rest?
K-time get resolution, HR timer resolution. That's
Really, an NSEC resolution, 10 millisecond resolution is too.
So we
too
want
low.
to.
Oh, yeah, it's too close.
Hmm?
No, yeah.
No, I mean for not for the CPUs but
No,
for the
yeah,
rest.
even for the other devices. For example, we know that some GPU can be power up or down in less than a millisecond time frame.
Okay.
So if you're using the 10 millisecond
Yeah,
tick,
you miss them.
you just don't miss it. So clearly, nanosecond, the problem is that either you have the tick or you're using time gate or local clock. So the tick is 2 cores, so you just use the other one. I agree that having 1 microsecond precision is not really useful, but you don't have something in the meantime. I mean, in the mean, you don't have intermediate value or granularity.
Yeah, getting the time is costly.
But clearly you don't need that for CPU because CPU idle is doing the same already.
Yes. Yeah, so there's
Or you
like
disable what CPU idle is doing. I mean, there are two, CPU idle and GNPD are measuring the same thing. So.
Well, it's using the same metrics, but it measures different things.
Yeah, you're measuring even more things.
Yeah, but I'm still using the same values. So.
Yeah, you're right.
So. Okay, so there is even more K-time gets being called, and that's because we're using runtime PM now for CPU devices. So that means that in the part of the idle, inside the idle path, we are doing a PM runtime get sync and PM runtime put sync when we wake up. That means that we go in and ask the runtime PM framework to do this reference counting and all that stuff, which means that there's a lot of code being executed in there, and there is K-time get, in this time K-time get monofastness being called, and it's being called several times. So there's additional framework improvements that needs to be considered to drop these calls to K-time get.
Can you compare with GFIS? I mean, if you...
We just converted runtime PM call to...
I know that the GFIS is not enough resolution.
Yeah,
but if we when you before because if you inspect the variable GFIS, it's almost free. So when you exit and you compare with the previous GFIS, and you see that you have an increase of the GFIS.
Yeah.
Maybe you can just accept that this resolution is enough. Using the clock in this time is not relevant. You use the clock if there is no change in the GFIS, but if there is a change in the GFIS, then you use the GFIS, even if you lose resolution.
Yeah, but you will waste too much time doing this test instead of directly reading.
No, why? It's just GFIS. just a checking of a value.
We have done when we have moved runtime PM on HL timer get and get. The difference between using GFIS and using get and get was not that much. We provided some numbers, some performance numbers, and the difference, and it was even worse.
Now what I'm saying is, instead of, I'm not saying that using GFIS always.
No,
I'm
using saying that when we moved from GFIS to cat and get, the difference was not that huge. And if you want to start to read GFIS and check if it works using cat and get, you will take more time than directly using cat and get.
Okay. I've been measuring the cat and get, and I know it's up to 100 and 120 microseconds.
That's the worst case.
In worst case, it's, and we are around. I don't remember the numbers, but I know that the average is around 40 microseconds to have a cat and get. At least with on the platform I did the test.
We have some value on.
It's on. I think it's posted on the mailing list as well. You have part of your series, so you can go back and look there and see what you have values.
So I don't see how just looking at the GFIS, which is variable, and do a comparison is more cost is the same that reading the.
It's the same. There is not that much difference. In the
okay.
You can have a look in the commit message. You have all the detail for 32-bit and 64-byte architecture. That's why we have decided to move runtime PM on HL timer, and we have moved runtime PM statistic on cat and get. So
No, I'm not saying that we don't use cat and get. I'm just saying that when we have change in the GFIS, we don't use cat and get. But when we have a change in the GFIS, that means we are in a lower resolution. We cannot catch the transition, so you use in this case cat and get.
Yeah, but the first thing is that in some case you will have a 10 millisecond granularity of few microseconds. So it's useless to catch some 100 microsecond difference.
But if your transition is taking more than 4 milliseconds, do you really care about computing microsecond if it takes more than 4 milliseconds?
No, but in your statistic, I mean, if sometime you're only at the 4 millisecond or 10 millisecond boundary, and if sometime you're at 100 microsecond boundary, why are you taking care of this 100 microsecond? Because you have lost dozens of this 1 microsecond in a.
I mean, it's not. It's about all the tree of the domains. So you do cat time get in every place. I'm correct or not?
For the domain level, we do
Yes.
cat time get.
So you do cat time get and see for each domain the time of the transition. So sometimes you will have domains doing changing transition. Okay, so you need to measure precisely the changes. But if you have domains which are changing less, you don't need such resolution, and you can check that with the GFIS. I mean, if in between entering and exiting, you have a GFI change, that means it's long enough, so you don't need the resolution of the timer. That just so you can save a few calls to cat time get in this pass.
Yeah.
That's just a suggestion.
Yeah. I mean, we can look into it and see what it, how it plays. But
See, if you for CPU, I understand that you need.
indeed.
There are a lot of transitions, so
Yes.
you cannot use GFIS. But if you have other devices, let's say, I don't know, a console or whatever, can take much more than. So, what is the point of measuring cat and get long period? You can just use GFIS in this case.
Because if you have a device that has some long period and some short period, you're just doing crap in your statistics. I mean, let's say that you have a device that that is idle 1 second, and then it is used with some less than 4 millisecond frame. In this case, measuring this less than 4 millisecond frame is just crap because you have already lost all your granularity in the long value. So You're just hiding something that you have lost in the other case.
But it's acceptable or not?
No, it's not.
In this case, it's like the timers. The timers are now it's the low res timers. When you have high long timers, there are not precise.
What we're testing is the edge timer precision, not the timer. In the case.
Only for devices changing a lot. For devices not changing, domains not changing a lot, you don't necessarily need this resolution. But, well, I mean, it's a suggestion.
Yeah. We can look at it. It might make sense in some cases. I have a few minutes left, so besides the K-time get in the runtime PM core, there's a lot of code that's being executed there. It's code that's needed, of course, for the general devices. But as I said before, CPU devices is quite special in regards to this. So the only thing that we actually need is the reference counting and invoking these callbacks. That's what we need. So we've been considering that maybe we should invent a specific runtime PM, backdoor, so to say, to do these kind of things that we only need and bypass a lot of the code, including the K-time get things. So that's another thing that also can be considered as an improvement to decrease this contention latency things. So yeah, if I recall correctly, I think even Lina posted some patches for this long time ago on the mailing lists. I don't think there was much review on that, but it's something that we could look into as an improvement as well. I don't have any measurements done on this, but that's also something that, of course, we should do. Any thoughts on that? Okay, so the current governor that we have invented for dealing with this shared idle states in the NPD is today only picking up when the next timer event is going to expire. And I've been following the work that Daniel has been doing on this next event prediction for IRQs and for the need risk get stuff. And in the next step of improvement, we'd like to get this kind of information to be considered in this governor as well, so we can get better selection of these cluster idle states. But at this point, we have taken a very simplistic approach to get things going and to start with something. That's why we have this next timer event, because that's the fixed information that we have. It's nothing that needs to be predicted, so we just get this information and consider that as the next wake up. But there's more information here that needs to be considered, of course.
There is a dependency between your work and my work.
Yeah.
Because when we want to do cluster idling, but from the CPU idle, because it's supported, we don't have to pass through the cluster idling. I have to know when it is supposed to wake up the cluster. So there is a dependency with the other CPUs, which if I am the last one, or I should, well, not necessarily the last one, but when I'm going to sleep, I have to put what will be my next wake up. And when the other CPU will enter the same state, the cluster state, they might check if the next wake up of the cluster, supposed cluster, will be long enough. Okay, and in this case, I need a description of the cluster power domain. I need to rely on the power domain, but is only for cluster idling. So how can we tie this information?
Yeah, that's a good question. I don't have the good answer. So, but yeah, it's your governor is like generic. It's not tied to cluster idling. Yeah,
but you will need to do the same thing. When you go to cluster idling, you won't go to cluster idling if you see that the other CPU is about to wake up.
I don't care about that on my code.
So
I have this lock, as I said.
no, but if you considering the target residency, you need to have the both CPU to be sleeping long enough to not break the target residency of the cluster.
Ah, okay. I see.
So if you are the last one,
yeah,
and you see that you can sleep long enough,
yeah,
then the other CPU, if you know that the other CPU is about to wake up, and the wake up is very soon, and you know that you will enter the cluster state, but the other CPU will wake up in the middle of the target residency before reaching the break-even. So you will be losing energy in this case. You need to have this kind of communication.
Oh, yeah. But so in this governor, I'm not considering one CPU. I'm considering CPU mask, which might be several CPUs.
So you have the next event for all of them.
Yes.
And you take the earliest one and you check the.
Yes.
Okay,
yes.
so we need to do the same, exactly the same. So we have to tie somewhere. We have to tie this information. We don't have to duplicate that, but we have to tie what you did with the GenPD,
Okay.
with the CPU idle governor, in case we are not passing through the cluster idling. We just go to cluster idling, but directly from CPU idle.
Why do you need that?
No, today we don't have the cluster idling. You use that on some platforms, but not all platforms.
Yeah, but why do you need the information in CPU idle? That's my question.
Because if we don't use cluster idling in this case,
Yeah.
I need the cluster thing information for the next wake up.
Yeah, to feed back into the
Yes,
prediction.
to prevent to enter the cluster state in case if another CPU is about to wake up.
Yeah, that's something we have to think about how to address.
Yes,
that.
otherwise we will have a duplicate.
Yeah.
Except that with the coordinated mode, you can't really do that.
Why?
Because,
No, it's in the process of idle state selection.
yeah, but right now in CPU idle, when you're using the coordinated mode, the C state that you're selecting is for the CPU, and that will be registered at PSCI level for this register,
Yes.
for this CPU.
Yes.
So when you're at the end, if you, let's say that you're CPU 0, and you say, okay, I can enter cluster off, but I see that CPU 1 is going to wake up, so I don't want that the cluster will be off. If you say I will be only CPU on, CPU off and not cluster off and CPU 0, you will prevent the cluster to be
This
off.
is what I'm saying.
But
Yeah.
now the CPU 1 is waking up and will enter a long sleep time, which means that you can pour off, or you should pour off the cluster. You will not be able, because CPU 0 say, I don't want to be cluster off.
Yes.
So you can't do that.
No.
So you don't really need this information at the CPU idle driver level.
But at the moment you enter, you select the state. You have to take the right decision. If there is a change in the right after you take the decision, you cannot
No,
handle
it's
that.
not a change. It's just that
A change of the situation.
you can't do that because the selection must be done per CPU with the coordinated mode. Otherwise, you will prevent some case where you could have entered. Only with the OS initiated, only if the cluster off state is decided by kernel, you need this cluster information. If you're using the coordinated mode, you will just set the wrong value to a CPU.
So that's a limitation for the
Yeah, that's a limitation of
for
the
the platform
coordinated
coordinated mode.
It
So-
makes that much more simple.
Yeah.
But otherwise, you will just set the CPU in the wrong state. Or you will say to the PSCI that this CPU should stay in the wrong state.
I'm not sure I get the point.
We can take it off.
Yeah.
Oh, yeah. Yeah, well.
So I have one more slides, and let's just take this very quickly. So one thing that is not supported today as well is that we cannot support several levels or several levels of hierarchy of clusters. So, and that is something that is actually not only limited for this particular use case, it's limited to MPD support is multiple idle states, and we only support 2 levels of that. So it's something that needs to be extended in the MPD anyways. There's even patches on the mailing list that's been pointing to this as a problem. So this is something that we need to deal with. So in principle, you have to propagate information about the state selection process on one level to the upper level and make a decision based on that. Today there is no information about it. It's only 2 states, on and off. So it's not really working on several levels, so to say. This is not a problem for those platforms that I've been working on, because there's only 2 levels. But it's quite easy to understand that this could be useful for several bigger hierarchies, so to say. So this is something that we probably need to look into quite soon. Okay, thanks everybody.